Hello everyone, welcome back to another video. In this one we are starting this new unit which is going to be based on the content covering temperature as well as the thermal properties of matter. This is also another alternative chapter name for this very unit. So when starting this chapter of temperature, it's also really important to start right from the top so that there are no confusions later on. So when we talk about heat or how hot an object is, in those cases we talk about two things, and in real life we may use these interchangeably. So as is written here as well, one of those would be temperature, which is basically, and this right now is not the definition, so this is the degree of hotness or coldness, right? How hot something is or how cold something is called the temperature, but keep in mind that this is not the definition of it, and we'll be looking at the definition in a while. So this is temperature. On the other hand, as opposed to temperature, we have heat energy, and heat energy, the more technical name for this would be thermal energy or internal energy. And again, this is also not the definition for heat energy. We can say that this is the amount of energy contained by any hot object. Now, if we think about this initially, it may appear to us that whatever has more temperature should also have more heat energy, or the technical term for this would be thermal or internal energy. But it's not always the case. It could be, but it doesn't necessarily have to be so. Let's have a look at one such scenario. So this guy right here is sitting in a tub of hot water, and inside that he lights a match. Right, so this right here is the match, and what he's sitting in is the hot water. So this is the hot water. Now if I were to ask you what's at a greater temperature, which one would feel hotter if we touch these, so obviously the match would be hotter. But if I were to also ask you which one has more heat energy, then you need to think about this a bit more carefully. So right now what we can see is that the hot water is also just based off the amount. This is much more, we can say that this hot water has much more molecules than the match, right? So this one will actually have more heat energy than just the match. Another way to think about this is also this, that just one match alone could not heat up this entire tub of water to a sufficient temperature, right? So if, for example, if the match is really hot, so we can say that approximately the temperature of a match is, let's say this is around 800 degrees centigrade, and hot water temperature is not even half of that. It would maybe be a value like 40 or at max 50 degrees centigrade. But because this has much more molecules, it would have more heat energy. So the heat energy does depend on the number of molecules, whereas the temperature does not. So these quantities, it's not like there is no link between them. There is a link between them, and this is what we'll be talking about now. So the idea is that a difference in temperature is what actually leads to thermal energy transfer, right? So if you have two bodies which have different temperatures, this is going to lead to thermal energy transfer. So even in this case, if we know that, for example, here the match was at a higher temperature and the hot water was at a lower temperature, so just based off this interaction, I know that heat would be flowing from match to the hot water. Now that is a separate argument whether it would be sufficient to heat it or not, but the temperature would be flowing from the match to the hot water. So another important idea to discuss here is that thermal energy always flows from higher to lower temperature. Right, so another important thing about this. So if this is like the first point and this is the second point, so obviously when thermal energy is transferred, there is some change in the temperature of the objects as well. So this continues until temperatures are the same. Right, so for example, if we have let's say a hot cup of tea which is placed in an air conditioned room, so heat is continuously being transferred from the cup to the room, so until the temperatures are the same, which is also called thermal equilibrium. Right, so when the temperatures become the same, there is no more thermal energy transfer. One last important point, and again we'll also see all of these through an example, is that the rate at which thermal energy is being transferred, so rate of transfer of thermal energy, is proportional to the temperature difference. Right, so whatever objects we are talking about, the greater the temperature difference between those objects, the faster the thermal energy will be transferred. Right, rate means how it's happening with respect to time. So keeping all of these in mind, let's have a look at an example. So let's say we have two objects like this. One is kept at 100 degrees centigrade and the other one is at 40 degrees centigrade. And now the heat energy starts, the thermal energy, let's use technical terms now, the thermal energy starts to flow from between these objects. So what we've written above, all of these points combined can tell me exactly how thermal energy will be transferred. Now obviously there is a difference in their temperatures, so there is going to be a thermal energy transfer, and it's going to be from the higher temperature to a lower temperature. So basically thermal energy will be transferred from the 100 degree object to the 40 degrees object. And this will go on until temperatures are the same, but let's also see how this applies here. Now this will not just be the case always. This is just me using a simple example to illustrate a concept. So as this one is transferring heat to the lower temperature object, what would happen is that this temperature would start dropping and this temperature would start rising. So for example, just following through with the example that we talked about previously, if we have a cup of tea which is placed in a cool room, so the tea would get colder because it's transferring heat energy to the room, and the room will get ever so slightly warmer. So it actually also depends on the mass as well as something that we'll talk about later called the specific heat capacity of an object, as to how much temperature change will actually be there. But let's, for the sake of simplicity, assume that this temperature drops by 10 and the other one rises by 10. Right, so this goes down by 10, this goes up by 10. And then again still this one is at a higher temperature than this one. So again this one will keep on transferring heat energy to the lower temperature object. So this might go to a value like 80, this might go to a value like 60. And again you can probably also guess that once this goes down by 10 more and this one goes down by 10, then the temperatures would be the same and we would have thermal equilibrium. So a further change of 10 gives you 70 and 70, at which you have thermal equilibrium. But I actually need to also talk about something else here, which is this. The last point which said the rate of transfer of thermal energy is proportional to the temperature difference. So if we talk about the different temperature differences that we see throughout this entire scenario, So initially the hot object was at 100, the cooler object was at 40. So the temperature difference would be 100 minus 40, which would be 60. Then if I talk about this case where the hotter temperature drops by 10, the cooler temperature rises by 10, what's the temperature difference now? So that would be 90 minus 50, this becomes 40. Further, 80 minus 60 would give me 20. And finally it also becomes 0. And as we talked about this is thermal equilibrium, so no more thermal energy will be transferred. But if I just look at this scenario here, I can clearly see that the temperature difference is reducing. So this also means that the rate, the speed with which thermal energy is being transferred, will also decrease, right? So since delta T is going down here, this means the rate of thermal energy transfer would also reduce, right? Because it's proportional to the temperature difference. So remember how we started off this video with the ideas of temperature and internal energy. So now let's officially define these. So temperature on a molecular level is defined like this. So this is a measure of the average kinetic energy of the molecules, right? You can say molecules or particles in a substance. So when the temperature goes up, and because we say that all matter is made up of small particles which are in constant random motion, those particles start to vibrate faster. And because of that faster vibration, the kinetic energy increases, right? So this is a measure of the average kinetic energy of the molecules. So when temperature goes up, we say that the particles move faster and the kinetic energy also increases. The internal energy, on the other hand, is defined like this. So this is the sum of the microscopic, and by microscopic we mean that of all the molecules. So it is the sum of the microscopic kinetic energies and potential energies of all molecules. And as we'll also discuss in the upcoming videos, this is due to their random motion. So in the upcoming videos, this will be stressed on more. What actually gives rise to the kinetic energy is the temperature, but what actually gives rise to the potential energy is something else, and we'll talk about that. And this is due to their random motion.